you. Good morning. The topic of my talk is pragmatic functional programming with Java 8. And very briefly, pragmatic, it's about adopting a slightly different way of thinking without getting overly stuck on what's pure FP and what are the principles behind that. Really just getting the job done with whatever tools we have available. Why should you listen to me? I've done Java for several years now, mostly working in the financial services and internet services before and after that domains, largely web systems in one form or another. For many years, also doing systems integration. Most of that has for many years been on the Java platform. So the reason the way that this talk came about was earlier this year, my team converted several applications and started one brand new application, all on Java 8. So we can maybe see how many of you are actually currently using Java 8 in production or in development. And that's, I'd say, probably about a fifth. And are you guys also using the new Java 8 language features that were introduced at all? Ish, somewhat. And are any of you using other JVM languages or otherwise that have a highly functional or hybrid approach to programming, such as Scala? There's the Scala cluster. Right. So why do we still bother with Java? I think that you can probably answer this for yourselves, but the reason why we're all here today talking about Java and not something else is the massive investment in the ecosystem. We all have tools and processes and libraries and training investment. And so while there's lots of new shiny options, some of them have been maturing quite nicely in recent years, Java still is, for many of us, a fact of life. In some cases, decisions just get made by sheer inertia. So maybe you could have evaluated something else in the process and picked a slightly different tool that'd be better suited for the task at hand. And I hope to a little bit later on get into some objective measures of what you might use to decide, rather than just your gut, which languages is appropriate for your next project. So onwards with Java 8. Java 8 introduced quite a few new features, largely centered around functional programming. And the reason why we want to bother with those is really the main angle that Oracle used to introduce it is about concurrency and the way that we wish to leverage multi-core is through removing internal control and moving that, giving that up, and better expressing our control flow logic by decomposing it into smaller functions and letting something else, such as parallel streams, for example, take care of it for us. And it has been said that Mutable State is the new spaghetti code. That's attributed to Rethink, who is the creator of Clojure. And the problem is that encapsulation in all of our existing object-oriented tooling doesn't really, tooling and design patterns don't really help with that. One thing that does help with that, however, is monads. So we're going to go in the opposite direction of abstraction this morning to the previous session. So a monad is an endo functor in the... Let me read that. Okay, so we're going to unpack this. I borrowed the slide, the idea for the slide. You do not need to understand monads to apply functional programming. And it might, however, be useful to unpack what they are a little bit. Why that is Java now ships with 3 of them that are hiding in plain sight in Java 8. And you will encounter them in the process of adopting the new features of the version when you do get to it. It's definitely worthwhile adopting Java 8, even for your existing projects. We actually moved some workloads without touching anything. And we actually rolled back a deployment because our metrics improved so much, we felt that we had broken something. So remember what Andreas was telling you yesterday, watch your performance metrics when you deploy. We did that, and we thought that we'd accidentally removed some code. That was very suspicious. It turned out that the Java 7 to 8 upgrade, purely on the runtime side, was that great. We didn't do anything else other than upgrade the JDK. So let me take a step back. We've all seen functions. You probably remember them from maths class. A function has an input and an output, and that input and output are completely immutable. Whatever you put in, you get something else out, and there is no state that's left behind in that function. So the way that Monads came about was actually in the pure functional programming community. They were struggling to actually achieve real results with this, because if you can't retain any state, how do you actually get any useful work done? A function doesn't really have, it doesn't really execute. You could replace it with a lookup table, but you actually want to achieve some side effect coming in and out of that function. So again, we take some value in, value comes out, great. The basic notion of a monad is really just a design pattern. And you don't need to understand anything more about monads than you do about, for example, the intricacies of garbage collection, or even the way that the JIT compiler works. Sure, at some point in time, maybe if you're creating your own, you do actually need to spend a bit of time and dive really deep, understand what you're doing. You probably do not need to unpack the maths behind it. For our intents and purposes, as mostly practicing software engineers working much higher up the stack, these are just design patterns. And it's a design pattern that allows us to chain computations in context. That's really all it is. And the way that it works is we're going to take some value and we're going to put it in a box, and the box is the monad. And it exposes certain mechanisms for chaining operations being done on it. And into that, the map operator, for example, we can pass in a function, and this is where the necessity for the lambda feature in Java 8 comes in. The application of that function will yield us another box, and that box contains the result of that computation. And why the box? What's great about the box is, for certain computations, if you're happy with the shape of the box that you're working with, you can keep going round and round this loop. And what this means is you can keep applying different functions to that box without caring about where those functions are. The box doesn't care, and the functions are all pure functions. So that's really it, a little bit hand-wavy explanation, but I hope I'm able to connect a little bit better than the Wikipedia maths page. Okay, so this is basically it. The map operator is defined by taking the value out of the box, applying a function that's being supplied into map, taking the result and putting it in another box. Which is great, but sometimes you actually have the domain of your function maybe doesn't yield a value in the same domain as the original input parameter. Maybe you have a function that wishes to emit itself another box. So in this case, it wouldn't work so great because we would have x in a box, but gets applied to g. G takes x, but actually yields another box itself. So we end up having a double-boxed value output. This is maybe great if you're moving house, not so great if you're just trying to get some work done by chaining functions, but this is where Flatmap comes in. And this is something that tends to confuse people. It really shouldn't. It basically just says, give me the box, I'm going to apply a function, unpack whatever's in its box, and I'm going to put that in the final resulting box. And this way, once again, you can chain functions that have this shape. So the three monads that actually come in JDK 8, this is my creative interpretation of them. We have a monad which is the option monad that can contain precisely 0 or 1 values in it. and it implements map and Flatmap and lots of other useful things. There is the stream monad, which basically stands for, it's a box containing 0 to some number of items in it, and it could be infinite. And there's one other box, which hopefully we'll get to later in the talk, which is the completable future monad. And the completable future is a special kind of box that holds precisely one value, but there's a little asterisk next to it. It says the value may or may not be there when you go looking for it, and when you do, it may also turn out to be a failure. So this is what that part's trying to say. It's a box that represents the result of an asynchronous computation, and that result may or may not arrive. It will probably materialize at some later time. Okay, here comes the fun part. So let's get warmed up. I'd like to start with this class, which is the demo optional. So at some point, we've all written a branch. Can everybody see this? Might look something like this. And in Java, we have to contend with the fact that the Java type system is really lying to us. When it says that there is a string optional value here, it really means there could be a string, but it could also be a null. And likewise with return methods, pretty much anything you call into, it could give you a null. It could also throw an exception on you. So that also plays some tricks when you start thinking more functionally. But this code should be instantly familiar to anybody, and you can probably already spot the bug in it. Going to save you guessing. If we go to the next version, which I have here, I've added a @nullable annotation on my string parameter to express the fact that my optional value coming in might not exist. And now IntelliJ or any number of static analysis tools will tell you this line right here could throw a null pointer exception at you. So you end up writing code that looks maybe more like this. So you have lots and lots and lots extra branches to protect yourself against those errors. And what's really getting a bit lost is that what we are trying to do is take some value that may or may not be there and do something with it, and then do that something might or might not yield a result in itself, and then transform that output. And this is where the optional box comes in. What we can do is we can take the value and we can construct a new nullable. And the of nullable static builder is basically our entry point into that box. We're taking a value, we're saying, hey, optional, give us a box for this. And it is smart enough to take that and wrap it for us. And if it, remember the slide, the box could be either have something or not have something. The value will be represented either as an optional instance of some value in it or an empty optional. And what we could do then is we could apply the map. So remember map, this is where we pass in a function, and this is the lambda syntax. I'm not going to go into too much detail. The lambda is being passed into it. It will only execute once the optional decides to apply that function on its wrapped value. It will unwrap it. If it's present, it will apply the do something computation. And do something, in my case, also returns, potentially returns a null. I've expressed that by actually marking that method as nullable. And because of that, I'm having to explicitly wrap it in a second optional. And maybe this is not so great. At first, when you adopt these features, you are going to have to play around to get a feel for them. But the next implementation shows us why Flatmap is actually useful. It allows us to basically save the need for unwrapping the box ourselves. So this is the or else operation. We basically saying take the resulting value of do something, wrap that in a box, and then optionally unwrap it with the intermediate default being the result of that in case it's empty. We could replace that quite easily with Flatmap, and the transformation option, so Flatmap will unwrap my optional here, and what you definitely want to do when you start experimenting with these things is get to know your ID quite well, and be able to debug and place breakpoints and things like that. The new ID 15 does quite well with that. Another little trick is to add a peek to these chain statements, which we'll get to in a bit. Okay. can't really tell, but you can't really tell by just looking at the code, but map expects that you do not throw any exceptions, check to otherwise you will abort the whole computation. And not only that, but we've also had to introduce this intermediate result. So the pressure that caused that to appear is because we now have this multi-stage pipelined function application. Almost imagine it as if you are piping several commands into one another in a shell. We actually have to record some additional information to carry the context from one function to the next. Because remember, we're trying to limit our side effects in order to gain the supposed advantages of this. So maybe we need a rethink. That does not look great. We started seeing this showing up in code reviews, and we had to basically take a step back and question why. I looked at lots of talks, and I looked at some of the books that were available already at the time, and much to my surprise, it seemed like there didn't really exist that many examples that showed a more complex application of these new language features and fundamentally rethinking your approach in how you're doing Java. And probably to people who've done functional programming for a long time, this would not be a surprise at all, but we really had to adjust our thinking. We had to start not just think differently in terms of these pipelines and the way that we approach them, but also how does that actually get realized in a Java context. In Scala, which many of you will probably be familiar with, you simply don't get some of these features. So to some degree, some of these problems, to some degree, I attribute the lack of those, or the issues that we're seeing with Java to simply teething problems. The fact that we are used to thinking in one way in Java, and simply because you got in the Java ID, you are applying certain patterns of thought that are maybe counterproductive. So a beautiful Lambda Zen garden turned out to look a little bit more like this. So maybe that's something that we can take away and to go back to the original implementation that will teach us, before we move on to the Java 8 functions, will teach us more about what are we doing wrong. And the first thing that I've done is, apologies for this, again, the code is slightly more complicated than your typical example, but it has to be for me to show you some of these problems that I'm talking about. In my original implementation, I was essentially mutating in place these lists, and the observation, I have a hunch that if I restructure this to a slightly more pure multi-stage approach before I even dive into streams, maybe this will help me better structure my final stream-based computation. So I start with two arrays still, two array lists, and I iterate, and I just have extracted a step that completes here, which sorts the IDs into two buckets. And if you squint just so, this is already almost a functional approach, because beyond this point, we do not modify these valid and invalid lists anymore. This is the result. So we started with one set, and we've come out with two sets. And likewise, in my second, I've pulled out a second loop that now iterates just over the valid IDs and processes those. Again, completely standard as we compile in Java 7, just fine. Just to show how this might, to make that difference a little bit more obvious, we could extract the ID validation, and this is where we start seeing this pressure to increase, to create new data structures along the way. Because my validate IDs function returns two sets of IDs, now I have to introduce a holder for those two sets, which in this case I'm using a library called Lombok. Is anybody using that? Yeah, it's awesome. So Lombok has a new annotation called value, And quick backtrack based on a number of people who reacted so positively to Lombok. Lombok is a Java annotation post-processor, and it's a new feature that got introduced, if I'm not mistaken, with Java 7, which allows us to save quite a bit of typing in producing boilerplate code. That is, it can tap into the Java compiler output, look at annotations in our source code, and produce appropriate bytecodes without us having to write those things. And where this comes really handy is in generating getters and setters and constructors and toStrings and Flint Builder APIs and things like that. And it has one of the fairly recent additions to it is something called @value, which basically allows me to create an immutable holder. It's basically a Java bean with just getters. One thing to note, although the validation result itself is not mutable, the lists contained therein might or might not be. That depends entirely on the implementation, which they still are since they are array lists. So the way to get around that is, if you're truly paranoid, you can wrap them in a modifiable list. And what this will prevent is anybody who receives this validation result output not be able to mutate my lists any further. And if you think back to the spaghetti slide, this really starts to get to the essence of why is functional really a useful approach. It's something to be aware of, something to know, and apply, even if you're not doing list or closure, even if you're not doing Scala, even if you're not necessarily doing the Java 8 features. That approach is actually quite valuable because it allows you to restrict the number of places where change occurs. So it leads to much, to call that is much more easy to reason about. And final evolution of the same method. Now I'm wrapping the retrieve remote operation, again, perfectly standard Java sugar for each loop, but now I'm also wrapping the result of that in an unmodifiable list. So what if we took some inspiration from this and tried to re-implement it using the Streams API all over again? Let me walk you through this. So here's what that might end up looking like. We once again start with the request IDs. So that's just me calling out and reaching for the list of IDs that's contained by incoming request. I get the stream of that list, and this is where this is the entry point into the new Java 8 streaming API. This is where the entry point is for existing collections. They're being retrofitted with a stream method, and you can apply functions to it, or in this case, I can simply apply a terminal operation, which is collect these the stream of things coming out and partition them by the result of a function call on them. I won't get too much into the syntax. The syntax is actually the easiest part. You will get the hang of it in no time. And what we've achieved here is we've actually split out the stream of IDs into, once again, two buckets. But because of the partitioning by collector signature, we are getting a map keyed on Boolean. Not the best way, but it is at least, should be fairly idiomatic to Java developers. We have a lookup based on a Boolean flag, true or false, and that gives us the partition. Next thing that I'm doing is I'm mapping that onto retrieving the remote result, and I'll get back to that in a sec. And subsequent to that, I am partitioning that based on the failed status of that remote call. And so on and so on. Going to skip over the transformation. Finally, I'm just collecting the list of failed and processed results, and I'm constructing the response the same way I used to before. The gotcha here is that we still have to be careful with that exception. If we throw an exception in the middle of retrieve remote result, our entire computation would abort. We'd have no way of actually knowing whether we'd have no way of, on item by item, deciding how to deal with our exception. in this case, part of the complexity arises by the fact that I want my API to return partial responses to the customer. So I don't want to just bail out once I encounter an error. I actually want to collect them, group them by their statuses, and figure out, construct a composite response. Again, this is where I wasn't really seeing enough in literature, not seeing enough in examples in blogs. Again, it's pushing me towards creating extra value objects that have to do with retaining state and passing that state from one function to the next. But I hope you will agree with me that at the very least, once we look at the main operation, once your processing shifts a little bit to this mindset of just applying a chain series of functions onto something, it is fairly easy to reason about. Okay, so we saw how the fact that we have some failed and some valid or invalid IDs introduce the need for these extra value objects. In some programming languages, Scala, notably originally in Haskell, there exist other monads to handle these kinds of things. And we have the either monad, which I'm going to show you very briefly, and the try monad. So basically the either monad can contain a left or a right value, but not both. And a try monad contains the result of some computation or the failure thereof. Fairly straightforward. Just a quick mention, tuples are also a functional language concept. Scala has a really nice implementation in the form of case classes. It has first class tuple support, as well as really nice value objects in the form of case classes. These don't exist in Java, so if in some cases we feel like we want them, we can actually get open source libraries providing that. I'll show you an implementation of that. It uses try first. Are there any questions on implementation? So we have, once again, we have a operation, we have a stream of IDs, we partition them whether they're valid or not. And the interesting thing here is the use of the try monad. So much like optional, it's a box containing precisely one value, but it doesn't let that exception leak out. So it will not interrupt our chain computation. It will just give us a result representing the success or failure of that computation. And it exposes its own is failed. Sorry, apologies, it doesn't. So we're still using the result. My result, essentially it's a Java pojo to represent whether that computation was a success or failure, depending on not whether the remote invocation resulted in an exception. Partly why I'm not just passing the exception around in the form of a try is when the computation fails, there is no way of tying that exception back to an ID. So in this case, I'm providing an extra function that allows me to keep the reference to the ID that failed and the exception that it caused. So the next thing that I'm going to do is I'm actually going to try and get rid of that duality using tuples. And the first place that I've done it is with the validated IDs. So here I switched to a library called Java Slang, and it provides an implementation of tuple, try, and pattern matching in Java. And I'm using its tuples to get rid of essentially my custom modules that retain the context from one computation to the next. So we have, yet again, a stream of validated IDs. And since this is now a tuple, the first component of that tuple is my valid IDs. That has also switched to, since I'm not showing you the imports, has also switched to using Java Slang's implementation of streams. It's a very, very similar stream API. It's much more inspired by the Scala collections, and it's a brand new open source project. So you probably don't want to be using it or counting on it in your production application just yet. it's merely here to illustrate some concepts. As my next step, once again, I'm retrieving my remote result, and that is wrapped in a try. The difference here is that, again, instead of returning a POJO wrapping that remote result and marking the success or failure thereof, I'm returning a tuple, an either, sorry. And remember that either can represent either a left or a right, and you will know which one it is. But in the meantime, you can pass it around without caring, and you can even apply functions to the left or the right selectively without actually caring which one it is. So this is a way to essentially streamline and chain these branching computations that fork and that reach on. Lastly, we are taking that stream of ethers and we are taking just the left side of that collection of ethers coming in, getting confused yet, and we're filing those away into the processed Pavel, and we're taking the right branch of the ethers and piling those into the failed pile. Finally, we can simplify this even further. Simplify. I've had to add some comments here for myself just to remind myself what this tuple contains. I have a tuple of a stream of strings and a stream of strings, and it is the result of partitioning the request IDs on there is valid, on the result of it is valid. Then taking the valid, that is the first element of the IDs tuple, and I'm mapping those onto a retrieve remote result, and I'm doing a fold operation, which is effectively a form of reduce. Reduce as in the map reduce, basically taking a stream and collapsing it down onto a single value. And I'm not, very briefly, I'll go into what the reduction looks like. Pattern matching is actually a very, very useful feature, and you see it a lot in functional languages. And here we're starting to see some of, again, the design pressure on those functional languages, why this pattern matching actually is necessary, why it has appeared. It's not simply to make your switch statements pretty. It is actually necessary to unpack these chained computations where you have a stream of things coming in and you wanted to decompose the incoming values into their components, make some decisions about those. Again, this is the it's match. It's implemented as a Fluent API, and the match object itself also happens to have monad properties. Besides the point, essentially we'd be saying when you encounter a left, that means that this is a success. With either monad, it's somewhat conventional to use the left half of the either as the success result of some computation on the right as the failure, not necessary always, but you see it a lot. So you're basically saying the reduced result function will take the existing list of things so far, that is my x's, and it's going to add one more x to it. So we're going to do a match on the x, and in case where it is a left, we're going to append it to the first half of the first element of this resulting tuple that we're building up, and if it's a failure, we're going to append it to the second tuple component, and so on and so on. And the stream itself will keep applying our reduction function until it distills that entire stream to just one value, and we can go back and receive just the list of two sorted results. And finally, I can construct this response just like so. So effectively what I have done is I've taken my nice idiomatic Java that would be instantly familiar to any imperative programmer for the last probably 30 plus years, and tried to write a fairly obscure, fairly different approach. Effectively, I'm trying to write Scala in Java. And there's nothing wrong with that. But it ultimately comes down to preference. One of the things that we saw very early on is that the people writing the code, for whatever reason, they felt like they were actually really simplifying things. You really feel like a hero when you go in and take a deep dive and you replace a bunch of for loops with this one chain stream computation that has a bunch of parameters mapped onto it. But it comes down to personal preference to some degree. I don't know how many of you are doing code reviews. Even if you're coding on your own, you've probably had this happen to you many times. You go back to a piece of code 2 weeks after you having written it, and you look at it and it's completely foreign to you. So this is actually happening quite a lot to us. We get these code reviews, and they probably, I don't know what my face looked like when I saw some of them, but it probably looks a lot like the blank says that I had from you earlier. It comes down to preference. I think over time, working with stuff more and more, you might find that you really enjoy the functional approach. There are benefits to it, I'll show you in a second. There are very, very practical benefits to it. But depending on the composition of your team, depending on the strengths of the individual team members, you might find that either you prefer the much more obvious imperative approach, or that you actually tend to think in higher order functions, and you tend to prefer generic data structures. And I think based on these two approaches, you might even be able to make a more informed decision about which alternative JVM language, or non-JVM language, please don't, would be a good fit for you. I find that people that enjoy this latter style of thinking, the more generic high order functions and generic data structures, tend to also lean towards closure and dynamic typing. And people that would much rather like the somewhat the approach that I took with that final example of having custom types and matching on them and decomposing them, but still using these chain computation ways of composing your program. They tend to enjoy Scala quite a bit, and Scala has some really lovely features like built-in pattern matching and case classes to do that. So like I said, code review really essential. The code has to capture the essence of your system, and it has to make sense to all the members of the team. The last thing that you want to do is look at some code because we're failing system at 3 in the morning and have absolutely no idea what that's doing. So, since this is talk on pragmatic functional programming, let me talk very briefly about performance. The reason why this is interesting is the first thing that probably springs to mind is all this abstraction is fine and great, and I'm not completely sold on the decomposition aspects of it, but what's it going to do to my performance? And like you heard earlier, JMesh is actually a really, really great way of measuring that. Don't listen to me, you should actually measure your own system, you should measure your own methods. But I'm going to show you the results of 2 methods that essentially compare the normal sugared for each loop to the stream iteration of it. And all that I'm doing here is I'm taking a list of evens, I'm taking a list of items which contains a series of random numbers. I'm filtering those to only the even numbers, and I'm adding that to a resulting collection. And the results of this surprised me quite a bit. What I have here is a graph showing the execution times in nanoseconds for these 2 methods, and a third, so the first 2 methods that I showed you just now are the blue and the green graphs are the imperative and the stream approaches respectively, and the bars are showing the execution time, so a shorter bar is better in this case. And what we're seeing is that there is essentially no performance penalty that you're paying for this. So that argument of whether or not this is binding much from a performance point of view, again, don't take this as your source of truth. Do your own measurement. It's really easy to do. But this surprised me chiefly because I actually did the same test a
couple of months ago, and the difference was actually much more pronounced in favor of the traditional for each loop. The orange bar here is the parallel stream implementation, so it's the standard Java 8 stream, and you can see that we're almost not paying, in fact we might even be getting a slight performance gain with 100 items in our input collection, and with 1,000 items there is a very definite performance benefit to it. Again, that's something that surprised me. I would have expected the cost of it to be much higher. The key benefit here is, I think, one of ergonomics. Essentially, for the developer, all that they have done is replaced stream in a statement with parallel stream, and the rest of the computation is being composed exactly the same way. So the benefit of thinking about functions and decomposing your system into a series of function applications, the benefit that you might be able to achieve, depending on the context, is that by externalizing the control flow, you can actually gain these nice benefits by not even having to think about what system am I on, how many cores are there, is it even worthwhile actually going in parallel. So under the hood, this all works using the fork join framework, which takes care of all those little details for you. And perhaps equally surprisingly, this next slide shows the garbage collection profiler being run on the same JMH benchmark. So effectively, this is showing my object allocation rate. The units in this case are bytes allocated per operation. So for every iteration of my benchmarked method, this is how many bytes are actually being allocated and are going to be reclaimed as garbage. And once again, the fact that these are roughly of the same length surprised me. I would have expected the parallel or the streaming implementation, at any rate, either of the streaming implementations, to produce a lot more garbage than that. So, any martial artists in the audience? Right? Yes, awesome. I really like this quote. Stuck it up there because I love it. I think the benefit that you get from thinking and practicing functional programming is this notion that getting rid of this notion that functional programming is something different, something that is a completely foreign approach to us. After a while, like I showed you in the very early phase of the earlier Java 7 style for loop, you can actually begin to see functions essentially emerge from what really isn't a functional programming language. And the benefit of composing your systems in this way, you can feel regardless. And to show perhaps a more considered mixed approach of the two, I have one final code example to go to. And it is this. So, hope you haven't forgotten about my little service completely. We are still doing, it's probably a derivative of one of the earlier iterations of it. I'm starting to validate my IDs. It's exactly the same as before. In this case, I've once again chosen to return an unmodifiable list because I'm paranoid. I don't trust my clients to not mess around with the values I return to them. I want them to be values, not just bags of things. I'm constructing a pair of that. Pair is yet another, in this case, it's just the Commons Lang pair. It's just like a tuple of 2, but it's slightly more friendly on the eyes in Java. And I am taking just these streams of valid IDs, which in this case will be contained in the left side of the this method is. Oh, there we go. So I'm just returning a pair of 2 collections, and the left element of this pair will contain the valid IDs. So at this point, I've chosen to actually take the stream of those valid IDs and map those onto a completable future. Completable future takes a lambda. We haven't spoken about it much. but effectively it's that box that holds the result of a computation that might take a while. And where does that computation actually take place? I'm passing in an executor that is being constructed in my class. If you're executing in a Java EE server environment, you'll probably find that there's a way to configure work managers and thread pools and actually get this injected into you. So it really is the reason why I've chosen to do so here is to create some amount of essentially a bulkhead and move the remote implications onto a separate thread pool and collect them. So at this point, the results might or might not yet be available. My computation is going to continue, and I'm creating 2 containers for it, and I'm creating a parallel iteration of those features. So now my features have all gone and trying to talk to a remote service somewhere, or on this separate thread pool. There's some network I/O going on that I don't wish to wait for. Maybe I've got other business logic to execute. Finally, I can take a parallel stream of those features and iterate over that, and I'm doing something completely non-advisable by documentation at any rate, but it is certainly possible. So I'm taking that stream, mapping it onto the join function of the computable feature, which basically says stop my current thread until this result is available, and give it to you, whether it be a success or a failure. And I'm doing essentially a side effect iterator of that resulting array. And if you look at the streams documentation, you'll probably find that the map and Flatmap and our friends are what's called non-interfering, require a non-interfering lambda to process the elements in that collection. But you could also opt for the old school way of just give me everything, and I'm going to make sure that I slot in the right container for it. And since I'm doing that on parallel threads, I'm having to use a concurrent friendly double structure. This is very low contention, so don't draw your eyes at the choice of implementation here. I'm basically just going and collecting all those results as they come in, using the default fork join executor pool. And finally, once again, I just construct my response. So my design choices along the way have been realizing that it's the network I/O that might take some time, and wrapping that itself in a box so that I can continue doing something else if I wanted to. And finally, going and using optionally, if available, if it's nice, if the fork join framework decides that it will be appropriate, go and collect those and collapse them back. Using a side effect producing lambda here, which slots them into their final values. So this to me is the result of several things. Having the knowledge of what the different choices are along the way. I've been able to, I think, come up with an implementation that gives me fairly straightforward, reasonable way to tell the story of what my process is doing, and getting some of the benefits where they count the most. Like I said, the network invocation, and then collecting those back into a single result. Questions on this?
So how often do you use the parallel streams in your production sort of application?
I would not recommend that. So it's something that I'm going to get back to you. So it's a valid call out. The reason why you probably shouldn't is that will default to the JVM wide fork join executor, and in a server environment, that's probably a bad idea. You might have hundreds of threads serving client requests, and they'll all go into the same thread pool. This is where the choice of, I think, application server versus more DIY Java container or containerless service. You have to be really careful about where you're actually placing essentially the queuing in your application. With I was going somewhere. So, in this particular example, what I'll do, if this were a real server application, I would probably explicitly manage the parallel streams of thread executor to. How often, it depends entirely on, it would be a design choice. If I knew that that result is likely of a size that would benefit from being parallelized, then sure, just there. I think the point I'm trying to get to is if you're armed with knowledge of the tools and you use a fairly functional approach to composing your system, you actually have those choices to make. If all you had in this case was a for loop that was calling my remote collaborator in a try catch block, I think I'd have a lot fewer options about that. So I think the cool thing about this stuff is once you start seeing things in that fashion, you start realizing that a lot of systems work in that same way. This is a slide from RxJava, which is the Java port of the reactive sanctions framework. And they're using what they call marble diagrams to illustrate the effect of filters. So really a filter is, I've got some stream of events and I'm applying a function, I'm filtering that stream on a function and getting a reduced stream out of it. Or I could map every element in that stream onto a different value. Or I could reduce the entire stream to a single value on a function. You start seeing this in other places like streaming computation frameworks like Apache Storm and Spark. You even start seeing it a lot of stuff that Dick Krebs and Martin Kleppmann have been talking about, essentially turning the database inside out and using systems such as Apache Kafka to replace your traditional database journal and then materialize that journal in a number of different materialized views as to be used as your read-only data sources. And once again, this is a streaming functional application over a stream of events. Yet another place where you see this a lot is in enterprise application integration, and it's something that most people rarely come across. But there's a wonderful book on the subject and a really, really great framework called Apache Camel. And essentially what they do is they start treating all kinds of data sources, including things like files and FTP servers as sources of events. And the way that you actually build up an integration flow is by composing these integration patterns that really what they are is a series of function applications on events emitted by source and then moving into a sync. So yet another example of this is, anybody here heard of Amazon AWS Lambda? Anybody used it? Awesome. The notion there is that you would create a function in language of your choice, you would upload it to AWS, and it would turn it into a container for you. And that container would fire up only on demand, only when you need to put some data into this. And the existing, there's an increasing number of event sources that support integration with AWS Lambda. But essentially what it allows you to do is, much like with the parallel stream example, we could completely remove ourselves from the mechanics of dealing with servers and where things are executing and simply define the function to be applied onto those events. So you can actually compose these really, really complex depth flows where events are coming out are being produced based on uploads of files into S3 or based on inserting records into DynamoDB, and you can have a function that post-processes those. The latest addition to that is the API gateway, which even allows you to turn a REST incoming invocation into a Lambda call. Yet another example of this is reactive streams and the actor-based with actor-based topologies. Essentially, you're doing the same thing. You have a very highly functional approach to decomposing your data processing system. So it really is about a change of thinking. The problems that I think we saw with the adoption of Java 8 features, mostly teething problems. We had to readjust our style a little bit, learn how to better deal with exceptions. Remember that refactoring and extract method also works equally well on lambdas, giving things meaningful names. But we did have to think a lot more about control flow and how to actually chain computations together. Martin and Pavel has some really great resources on collection pipelines, and I highly recommend that you go and take a look at that first before you start enthusiastically adopting streams. But that change of thinking, I think, in the long run will be very beneficial to the Java platform, especially I think as we have a lot more competition from the upcoming languages. I think based on where your team takes this and how you enjoy using it, you might find that you are now armed with the knowledge of what would be a better language to transition to in time. And you might just find that really Java is actually just fine. It supports enough of all the different paradigms. It does not really excel, as we have seen, in a highly functional approach. If you enjoy that, you will probably find yourself gravitating more towards alternative JVM languages if you still have a need to interoperate with Java libraries. But I think the overall benefit to you as a systems designer will be seeing the world in this slightly different light. Taking questions if there are.
Hi, Pavel. Yeah, just had a question about something that you mentioned, the optional type that was introduced in Java 8. You said that it's not recommended to use it like as a parameter type or return type. Yeah, can you expand on that? Because I was ready to like put it everywhere in my code.
It is something that we also grappled with. The tendency is, once you discover it, I think that just is great, and I like to sprinkle it everywhere. Some of the JDK authors are on record as saying that they really did not intend for optional to be used in that manner. My personal feeling is that it's probably fine to use inside your own internal APIs. If you have a bunch of private methods or something like that, maybe it's useful there. I'm not so sure about public APIs between packages or between classes. The reason why I say that is you tend to have, especially if you start using it in Java Beans as properties, wrapping everything in properties, it just starts to look really messy. Unfortunately, there's no good answer to this. One alternative to this, and I touched on it a little bit briefly in the talk, is using the Nullable not null annotation and using tools like findbugs to help you with that. There is something else that can also help you with this. It is the checker framework. It was research done by Washington University, and what they've done is they've annotated essentially the JDK itself and a large set of common open source libraries with nullability annotations. And if you use their compiler plugin, it extends the Java type system to essentially treat the assignment of a nullable variable to a nullable expression to a not nullable variable as a compile time failure. So maybe those are some of the things that, if you want to adopt it en masse, would be useful to do. The other thing is, I think I had an example in my optional demo. If all of this was a simple if-else branch, then perhaps the pulling out the monad and putting something into the box and applying a function onto that and pulling it out might not be worth your while. The traditional Java approach in that sense works just fine. It really starts getting valuable when you have a series of computations that you'd like to chain that are all operating on that box. And again, whether or not you even have that many functions that can operate on the value within the box, it's something that's highly use case dependent. Does that help?
Just another couple of things about optional. It's final, so you can't extend it, and it's non-serializable. So if you ever use it as a field, and you serialize that whatever you have object that you're including, it's going to be excluded from it. So it has a few sharp edges. So it's very nice, but it was built with a very, very, very specific purpose in mind.
That fold method you used, would you recommend using it, or should I just use something like Apache Spark or Storm?
Could you repeat the question?
For that fold method, I saw it. I've never looked it up before, but how's the performance?
Filter.
Fold.
Fold left.
Format protection.
Oh, format.
Yeah.
I see. That's just the standard Java string format.
No, fold
No,
left.
fold. You had a fold.
Oh,
method.
fold. I see.
Format
Okay.
protection.
Sorry. So that is one other of my sleights of hand in this presentation. So the fold method is traditional FP approach to essentially collapsing a list of things into one result. And it is sadly missing in the standard Java 8 stream. So what this particular implementation I'm using here is the Java slang implementation of stream, which borrows heavily from Scala's collection frameworks. So Scala also has fold left and fold right, which will collapse the collection from either side. I can't imagine any reason why this shouldn't be. Ultimately, once you compile it and the JIT has had a go at optimizing it, it will probably ultimately yield the same code.
Should I rather use Spark or Storm to do something like that, or?
It depends on whether you want to distribute your computations. That's the second half that I didn't get to. With something like Spark or Storm, you're implying that you have a data set that is large enough that you want to distribute to multiple machines. In this case, this particular stream implementation is not capable of doing that. It is just another way about talking. It's just another way of talking about an in-memory collection of things inside the JVM. So in that sense, it really is no different to the built-in list, or it's more like the built-in Java 8 stream. It just has some nice extra utility functions. Once again, though, because of its nature, it is capable of parallelizing itself and running the function that you supply, provided that it's reasonably side effects free, and accelerating your computation within that one JVM.
Thanks very much to Pavel.
Maybe I'd just like to wrap up. Two books that have been quite helpful to me are these two, Java 8 Lambdas and Java 8 in Action. Once again, the Java 8 massive online course, really, really great stuff. And Martin Fowler's
I think that course was taken offline on the 12th of August.
Oh, No,
it's
I
still-
believe that there's another iteration of it being coming, but you can still find all the lectures on YouTube.